today's topic is telescope. Tele is distance, scope to see. When we want to see the objects at large distance, then we use this equipment. So this device, telescope, is used for seeing distant objects close to us and magnified, so that their image is very large and we can resolve it better. We can see all the internal parts through the telescope. How the telescope is formed? To form the telescope, basically it's a very simple thing to understand. We have learnt about in the previous lecture a simple microscope. What is a simple microscope? It is only a convex lens. We call it eyepiece in microscope. In compound microscope, it is a simple microscope, and anything kept within the focal length will appear to be large. This we have already done, that this will appear to be large. Okay. So this simple thing we use. What is this? This is object. Now what we do, we have to see a star which is far away. From the star, many rays are coming to us, and those rays we will collect at one place. That one place is this. So what is this? This is image of a star, or image of something which is far away, and this image is again magnified by this simple microscope or eyepiece. Okay, this is our principle. Now there is one problem. The problem is, if this size is 1 and this size is 50, then what we find, that the brightness of this image has reduced. How many times? 50 times. So if this was having 50 rays in 1 centimeter, the same 50 rays are here, but those 50 rays are in 50 centimeter. 1 ray every centimeter. The density has decreased. So this will appear dark, while this is bright. So what happens? We see a star, it is bright. When we see it through telescope, it is dark. Why? Because the same brightness we have magnified, the number of rays are same, but the size has increased, so their density has decreased. Now what is solution for this? There is a solution. The solution is that this image which we formed here we have used only 50 rays. Somehow we will make it 500 rays collected together. Very bright image. If these are 500 rays and now these are here, so every 1 centimeter there will be 50. Every 1 centimeter there will be 50 rays, and we can see it quite bright. But for this, what we need? We need this object should be having very much light. Should have lot many rays, a large, this should be very bright. It should be shining. How this can be done? Now this we want to do for a star. One star we will make image. This image should be very bright, and this image we will see through an eyepiece. It will appear to be large. So this is how we make it large. Now how to make this? There it should be bright, so what do? We use a large aperture lens, and this lens is a let us say this time, this is towards the object to see the star. So this we will call objective lens. This is principal axis. This we make large aperture. That is its specialty. large aperture. Aperture means this diameter. Okay. Because of this large size, the rays coming from the star or from the far away object, the number of rays are much more, very large. Okay. All these rays are connected together. They are coming parallel and they will gather at the focus. Now to do our calculations easier, what we take that the rays are coming from a certain angle. Let us say like this. Because they are coming from a distance, they are supposed to be parallel. The parallel rays meet at focus. If they are parallel to principal axis, this way, then they will meet at a point on the principal axis, and this is what? Focus. But if they are coming like this, if they are coming parallel to each other but not parallel to principal axis, then what will happen? They will again meet at the same distance f. Same distance f here, but this ray going through optical center will go straight. This is converged, and they meet here. If some rays are coming like this, the parallel rays, this will go straight. Now this will go here, get converged. This will get converged and they meet here. This meet here. If they are parallel, the parallel will meet here. What we see? That there is a plane going through the focus. If any parallel set of rays, all the rays will meet at any one point of this plane. The name of this plane is focal plane. Focal plane. What is this? This is focus. So focus is on the principal axis. Otherwise, with the same distance, all the points put together become a plane and we call it focal plane. So the rays coming parallel from any direction will meet at focal plane. The same thing happens here. These rays coming here, if here is the focus, this is focus of objective. And here these rays will meet. And they will form an image here. Let us say this is the image. Okay, we give the name of image as A dash, B dash. A, B was the object somewhere at infinity because it is sending the parallel rays. It is a star or a faraway thing. Okay, this is the image formed. Now the brightness of this image depends how many rays have been collected, and the number of rays depends upon size of this lens. So we keep it quite large as possible, as much as possible, so that number of rays come here and it becomes a sharp image and very bright image. Now we want to see this image, but it's a very small image. We want to make it large. So we keep a eyepiece here. This is the eyepiece, and this we observe through this eyepiece. When we observe this through eyepiece, then where the one which goes through optical center goes straight without any refraction, without any deviation. The other one which goes parallel will pass through after refraction, it will pass through focus. Now this we keep in such a way that this point is at a distance of its focal length. This is eyepiece and this is the focus. We slide it in such a way that this distance is equal to focal length of eyepiece. And this point The focus of eyepiece comes here. Now anything in the focus of a convex lens, after refraction the rays become parallel, that we already know. So now this image is at the focus of this lens, therefore the rays going from here will become parallel. We can make it like this, and this one will go through focus, but these two will be parallel. Okay, when these two are parallel and we put our eyes here, we put our eyes here very close to this lens and see. Now where do we see the image? These rays are coming parallel, and for the parallel rays, what happens to the eyes? The eyes are relaxed. So this is normal condition of the telescope. This is first normal condition, normal setting of telescope. Okay. If we are observing it here, are we really seeing this object large? The answer is yes. We are seeing it large. What is the proof? See, there is a proof. Their magnification is done. How magnification is done? We have seen two formulas for magnification. One formula is size of image divided by size of object. Other formula is angle made by the image divided by angle made by the object. That gives the formula. Okay. Now we will use that angular magnification formula here and see, this is image, this is object. Object is making an angle here. Let us see, this angle is alpha. If this angle is alpha, where is the object? Object is far away. It is so much far away, for that object the distance of this lens and the distance of this lens and the distance of eyes, it is almost same. If the rays are coming from sun, it doesn't matter this distance or this distance, it is same. Okay, the same thing is here. So what we can say, the alpha is angle subtended by object on the human eye. Don't get confused that eye is here and the angle is here. I already told you both can be taken at the same place, because for that star millions of miles away, it is at the same place. Okay, so alpha is angle made by the object. Now where is the angle made by the image? Where do we see the image? We see the image here, somewhere here, where at infinity. And what is the angle it makes on the eye? The answer is, this is the angle it makes on the eye, this beta. Now beta is the angle made by image, alpha is the angle made by object, and we find this alpha is small, beta is large. So magnification, magnification M is angle by image divided by angle by object. Angle where? Angle made on the eye, that I have not written, it will be very long. So angle made by image, angle by object on eyes. So M is equal to beta upon alpha. But how do we measure it? We don't understand this language, we can't measure this. What we know? We know focal lengths. Focal length of this lens, focal length of this lens. So we want to convert it. Okay, we do a little derivation for that. For small angles, beta is equal to tangent beta, alpha is equal to tangent alpha. Therefore, magnification M is equal to tangent beta upon tangent alpha. Okay, from here we see what is tangent beta equal to. Tangent beta is equal to perpendicular upon base. If this is, let us say, O1 and this is O2. Okay, then this distance, let us say the length of this image is I. So I upon B dash O2. This is the tangent of beta. Again, this distance B dash O2 is equal to what? Focal length of eyepiece. So this is focal length of eyepiece. Then what is this distance? This is focal length of objective. Again come here, tangent beta I upon Fe. So this I will write I upon Fe. I upon Fe. Sorry. Focal length of eyepiece. Focal length of eyepiece on this side. If I put this value, this will be negative. Okay, I tell you in detail. This is I upon B dash O2. B dash O2. And what is tangent of alpha? Alpha is equal to this angle, opposite angle. So this angle is also alpha. If this is also alpha, what is its tangent? Perpendicular I upon base. Base is B dash O1. B dash O1. This is equal to. Now we put the values. If we put the values, putting values, B dash O2. B dash O2 is equal to focal length. But the focal length, positive focal length is on this side. So this focal length will be negative when we place the value. So this will be M is equal to I upon minus Fe upon, this is I upon B dash O1. B dash to O1. This is focal length of objective. Focal length of object. This is equal to, now this will become FO upon FE. This is our formula for magnification. Focal length of objective and focal length of eyepiece. This is a very significant formula. What are the indications from this formula? इससे आप क्या रिजल्ट निकाल सकते हैं? Number one, magnification is negative. Negative means what? The image will be inverted. This gives direction, and here you see the image is inverted. Okay. FO upon FE. FE should be as small as possible, and FO should be as large as possible. FO should be very large. Okay, the larger it is, the more is the magnifying power. So this is magnification of telescope, but in which case? Normal setting. Normal setting, that means the eyes coming parallel to the, the rays coming parallel to the eyes are relaxed. This is normal setting of telescope. Now the second setting we will see is the setting for distinct vision. When we want to see the objects larger than this, and it should be more distinct, resolution should be more. Is there a setting? Yes, there is a setting. You have already seen it in microscope, and in that, where do we form the image? We form the image at distance of distinct vision, that is D. For that, what we will have to do? What we have to do? We have to slide it, the eyepiece, little closer. Then what will happen? This Fe will become here. When Fe become here, then this image is between focal length of and optical center. focal length and optical center, this object for this lens has come between there, then it will form an image at a distance D. That can be done. And how will be that diagram that you have already seen? Okay. Now the ray which is going parallel to the principal axis will pass through focus, and now we have slided it this way. So this is small, this is large, and it will go in this direction. This direction. And where will be the image formed? Image is formed here, and this large is the image. A double dash, B double dash. Now this image, by the adjustment of this lens, we adjust this U in such a way that this V, the distance of image, become equal to the least distance of distinct vision D. This we can do by moving this. For this motion, we fit both the lenses in one pipe, and one lens in one pipe, other lens in other pipe, and one pipe can go inside the other pipe. This arrangement you have already seen. It's a very simple arrangement. Rack and pinion arrangement we call it. Okay, so this image we form at distance D, and now we see it very distinctly, most clearly this way. Now we will calculate what should be the magnification of this. So magnification, angle by image, angle by object. So M is equal to beta upon alpha. This is equal to tangent beta upon tangent alpha. Now tangent beta here. Tangent beta in this case is I upon B dash O2. I upon B dash O2. This is to be divided by I upon B dash O1. B dash O1. Okay, so magnification is B1 B dash O1 divided by B dash O2. This is equal to, now we put the values. Put values in terms of F, U and V. How do we get here is B dash O1. B dash O1. This is focal length because the parallel rays are meeting here. So this is focal length of objective. We write it focal length of objective and it is positive. Divided by B dash O2. B dash O2. This image made by the rays act as object for this lens. If this is object for this lens, then this distance will be termed as U. U for eyepiece. I put E here. U for eyepiece. Now this is on left side from where the rays are coming, which is our positive direction. The positive direction is the direction in which rays are going. So this is positive direction. Now we are measuring it on this side. If we are measuring it on this side, then this UE will be minus. So B dash O2 or O2 B dash is equal to minus UE. So this B dash O2, now I will put as minus UE. This. Okay. Now we don't want to stop here because UE we can't measure. So we have to find something for 1 upon UE or FO upon minus UE. For that we take this lens singly. This is a lens Where is the V? This is the V. For this lens, B dash O2, B dash O2 is U. Okay, then this value A double dash to the lens O2, A double dash to O2, this is equal to D. D. This is what? Distance of image. Distance of image. This is object for this lens. This is image for this lens. So this is equal to U and this distance is equal to V. When we put the values, both are on this side. So this will be minus and this will also be minus. This is what A double E, this is B double dash to O2. B double dash to O2. Okay. Now this is U, this is V, and it has a focal length. That focal length is how much? Focal length of eyepiece. And we know a relation. What is the relation? 1 upon V minus 1 upon U is equal to 1 upon F. Now let's put values. Put values for which lens? Put values for eyepiece. So 1 upon V will be 1 upon minus D. Minus 1 upon U will be equal to 1 upon minus U for E is equal to 1 upon F, 1 upon F E. Okay. Now this minus and minus will be plus. We leave it here, transfer it on this side. So this will lead to 1 upon UE is equal to 1 upon FE, and this will go there, become plus 1 upon D. 1 upon UE is equal to 1 upon FE plus 1 upon D. Okay, 1 upon UE. Here, see the equation 1. This FO upon UE. So let us multiply this thing with FO. Now this will become what? FO upon UE. FO upon UE. Multiply with minus also. Minus. So this will be equal to minus FO upon FE. FO upon FE plus FO upon D. This is value of minus FO upon UE. This value FO upon UE is what? FO upon UE minus is magnification. So we have calculated magnification here. So we write it clearly now. I will make it pretty clear. Once again, 1 upon UE was equal to this, multiplying both the sides with minus FO. So this is minus FO upon UE is equal to minus, we keep common, and this will be FO upon FE, FO upon FE plus FO upon D. FO, no, sorry, FO upon UE. Where is FE? This is FE. FO upon D. Okay. So this is magnification. So this is our formula for magnification. If this is our formula for magnification, can we make it more simplified? Yes, we can make it more simplified. This we will write as magnification from equation 1. From equation 1, we write it as magnification N. This is equal to, here you get FO common out, minus FO. And let's get FE common out, FE. But you will say there is no FE here, no problem. we will multiply or divide. So this will be FE. We will make it FE, FE. This FE we have taken common. FO we have taken common out. What is left inside? Here will be only 1 and this plus, and here we will have FE upon D, because this FE both have come out, this FO both have come out, so FE upon D. Here we have done FE upon FE. You understand? It's very simple mathematics. So FE upon D. This is magnification of telescope. In which setting? In the setting of distinct vision. So for the setting of distinct vision, I will write it here. This was normal setting of telescope, and I will write here second for setting of distinct vision. M is equal to minus FO upon FE M is equal to minus FO upon FE 1 plus FE upon D. This is our formula for magnification for setting of distinct vision. Okay, and this is the diagram for distinct vision. So you have to remember both the diagrams, this and the earlier one. In the earlier one, the derivation was very simple, very small, but in this one, the derivation is bit longer, and again I tell you the clue. Write this same thing. Magnification is image upon object. Distance of image, distance of object. Now this distance of, we have converted with the tangent formula, it has become FO upon UE, leave it here. Now again, for 1 upon UE, go for this formula. Which one? 1 upon V minus 1 upon U is equal to 1 upon F. This for eyepiece. Okay. So remember these steps. This will be here 1 upon UE, isolate it. Then multiply this with FO so that you get the expression for magnification. This you will get here, and this will come to this expression. FE will be here, D will be here, no problem. So this is magnification. Okay, this is done. Now, once again, in telescope, what are the specialties? Compare with microscope. In microscope, this is a small one, this is a small one. In telescope, this is small, this is large. Why? Okay? The question in the examination is asked, in telescope, why do we use a large objective and a small eyepiece? Answer. Number 1, the objective used is large because we want maximum rays to be collected from the faraway object. We want more and maximum rays so that our image is bright. This is for large. While the eyepiece should be small. All the rays which are coming from the eyepiece has to enter our eyes, and eye's pupil is very small. And what we want, all the rays coming should enter the eye in a small pupil. So how should be the lens? The lens should also be small, so that all the rays coming to the lens enter our eyes. So that lens we take small, and this we take as large lens. Okay. Now there is another term. What is meant by length? Length of telescope. Length of telescope. This distance is focal length of objective, and this distance is focal length of eyepiece. this. So what will be the total length, lens to lens? The total length is FO plus FE. Now here FO, just now to make the magnification large, how should be the FO? The answer is FO should be large. If we make a large FO, the length of telescope will go on increasing. That is why you see the earlier photographs of telescope which are made in large pipes, very large pipes, because the lens we fitted as objective was almost plain and its focal length used to be very large. Therefore, we had to use a pipe, but then it becomes inconvenient. So we have to put limit somewhere. The length is taken as limited length, and after definite length we fit it. So the length has to be FO plus FE. This is about length of a telescope. Now this type of telescope, are there any other variations? The answer is yes, there are many variations of telescopes. But so far you have understood how the telescope works. There is another difference between microscope and telescope. Microscopes, small things, large. Here also large, but a small image of the faraway thing. So this is used for faraway objects, and microscope is used for nearby objects but which are very small. The faraway object is star. A star appears to us very small. So it is a small object but far away, not in our approach. Use telescope. We have a small object, a cell or something which is close to us but so small that we can't see that. So we will use microscope. So this is the difference between use of telescope and microscope. In the construction, what is the difference? In the construction, the difference is FO for microscope is small, because the formula for microscope is 1 upon FO FE. This is for microscope. And for telescope, it has come FO upon FE. FO is in the numerator. So in microscope, FO should be small. In telescope, FO should be large. This is the difference between microscope and telescope. Microscope, these two are small, so the length of microscope is small. In telescope, this FO is large, so the length of telescope is large. Can we use telescope in place of microscope? If it is reversed, answer is no. We cannot, because these formulations we don't get in that. Okay, so this is working of a telescope and the necessary parts. Now we will see the different type of telescope. Is there any defect in this type of telescope? First I will discuss one or two things. This type of telescope, you see that magnification has come negative. Negative means the object we see in image, that is inverted. If it is inverted 1, would you like to see that? Answer is, doesn't matter. We have not seen the Mars. If the image of Mars comes to us and if it is upside down, it hardly matters for us. So this is used for astronomical objects. And if we want to straighten it and we lose the brightness, then we are paying a high cost. Brightness we cannot lose at any cost. Otherwise, we will not be able to see that. So we don't use anything in between, and this is used for astronomical distances. So this is called as astronomical object or astronomical telescope. Is there any other one? Yes. If we want to see the things on the ground, things on the earth, on the terrestrial ground, then if we see a building upside down, if we see a man upside down, that will upset us. We will not like it and it will confuse us. So we want to see the things erect and straight. For that we make some modifications in this telescope, and we see that this image which is becoming inverted will come straight. Can we do that? Yes, we can do that, and in that case its name will be terrestrial telescope. Now, what is the difference? How can we make it? See, how do we make it? Okay, first I will make a classification. Telescope. There are basically two types of telescopes. One is refraction type, which will use the lens, and the lens is doing refraction. Other one we are going to study is reflection type. These are two basic classifications. In refraction type, we have just studied one, that is astronomical. There is another which is terrestrial. There is another which was made by Galileo, so that is Galilean. So Galilean, terrestrial, astronomical, all are made by lenses, and in the lenses there are reflection type. There is basically one, but the two persons did it. One was, of course, the great man Newton, and the other was Cassegrain. So the Cassegrain made Cassegrainian reflection type telescope, and Newton also Newtonian telescope. Okay, so this is basic what we have studied, the principal astronomical telescope. That is the basic principle, and that basic principle is for every telescope. Only construction differences are there, small differences. So with the nomenclature I will introduce you with all these different types. What are the differences? So three types refraction, and these two types reflection type. So first, what is okay, see, this is the terrestrial telescope. This is objective. The rays are coming here, parallel rays, and the parallel rays meet at the focal plane, and we get a bright image, A dash, B dash. But this image is inverted. Now here is our eyepiece, which will make the magnification. One more lens is inserted between eyepiece and the objective. This lens. This is lens A. What does it do? We place it in such a way that this image is at a distance of twice the focal length. Now we know if the object is 2f, then where will be the image? The image will also be at distance 2f. So here the image is formed at a distance 2f. So how much is this distance? 4 of f of this lens A. Now but what has happened? The image is inverted for a convex lens. The object is placed at 2f, the image is formed, and the image is inverted. This was inverted image. It is again inverted and it has become erect and straight. Now we see it from the eyepiece, and the eyepiece magnifies it. If it magnifies it, then what is its direction? The answer, it is erect. Now we can see this far away object erect and straight. This is how we make terrestrial telescope. Okay? If this can show us the things straight and erect, why don't we use it in astronomy also? The answer is, more are the reflections, more it passes through different mediums, it loses certain brightness. There is some absorption of energy here. So the brightness becomes a bit less. From this to this, the brightness becomes less, and for in astronomy we cannot afford to decrease the brightness. Otherwise we will lose some details. As such, we get very small quantity of rays from a star because it is far away. So there is no use seeing it upside downside. To us it does not make any difference. So we remove this, the length becomes small. Otherwise, this length, how much is this length now? This length is equal to FO plus 4FA plus FE. It is a very large length. So the length is, number one, the length is not practical, impractical. Number two, we lose certain brightness here. So this is the disadvantage of terrestrial telescope, and that's why we don't use it much. We use astronomical for astronomical purposes. In Galilean type telescope, this is our objective lens O. It will gather the light rays coming from the faraway object, from the stars, and they should meet here. But before they meet, we place a concave lens here. What does the concave lens do? Concave lens will diverge the rays. So these are coming here and it makes them parallel. No, I will correct it a bit. It will make them this and this and this. You see, this is diverged, this is diverged, this is from the center, it goes like this, and here we put our eyes. Now if we put our eyes, what do we see? This here, 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 all these are parallel. So this is telescope set for parallel rays. If we increase it little on this side, the diversion will be more and the rays will meet at distance t. That will be for distinct vision. But this is a concave lens. This is used for diverging. If we make it little more like this, then it will be this way, it will be this way, and these two will meet here. We will see an image here. So this image here, or if we take it far away by making the adjustment, then we will see image here. This image will of course be larger than the point image made by this. This is making a point image, and because of this we see a large image here. This is by using concave lens. You can try it by making the diagram and you will be able to make it. This you won't find in many books. Maybe in NCERT it is not there. Only name is there. So this is how it is placed. The location of this concave lens is before the focus, not after the focus. So there is no real image formed in this. So this is only virtual image we see, and virtual image is erect. This is benefit of Galileo's, but its magnification is less. Its magnification is less, Fe is negative. Okay. So this is not much used for astronomical functions because its magnification is quite less. So this is Galilean telescope, and normally what you see in the market, the binocular or so, all these are made on this principle where we see the image as erect. So this is how we make the image erect. Okay. By the time we found that there are many defects in refraction type of telescopes in which we are using lenses. What are the defects or what are the shortcomings? The first shortcoming is the telescope, this type of telescope may have some color aberration. That is, we call chromatic aberration. Aberration means defect. Chromatic aberration. What is chromatic aberration? We have studied in the lens that each wavelength is refracted by different angle. Each wavelength means each color. Every color has got a different wavelength. Make it the other way, different wavelengths are called different colors. So the different colors get refracted by different angles. So, which is refracted most? The answer is violet is refracted most. So, this is violet and this is red. Here, this is violet and this is red. And this was white. Now you see, where does it focus? The blue focus at one place, the red focus at one place. Here there will be a blue image this way. And here there will be a red image. The colors are separated. Now when we see many images. One is blue, one is red, one is green, one is yellow, whatever. One is less, one is more, because this light may contain different colors. So they are all mixed up. One here, one here. So this color aberration mixed up the things and we are not able to see them clearly. We don't see them clearly. So this is one problem in this type of telescopes where we are using lenses. What is the second defect? Okay. Second defect is focal aberration. Or we call it spherical aberration, because this is due to sphere. Spherical aberration. Even if we are sending light of one color, here, here and here. The one which is going here, all are parallel, but the one which is near the corners will meet here. The one which is here, we find that curvature is less here. It is almost like plane. So the refraction is a bit, very small quantity, a bit less here. So they will also get reflected but meet here. This point. Where do they get the image? We get the image here, as well as here, as well as here, as well as here. At all the points you get the image. That means image is not very sharp. This is because it is spherical in nature and here the corners are more prominent. This defect of the lens, making not a sharp focus, is known as spherical aberration. So there is chromatic aberration, making the colors separate. There is a spherical aberration, making the focus or the image not clear. This is blurred. Though in very small quantity, but it does happen. And when there is a question of telescope or microscope, this makes a lot of difference. It should be very, very, very sharp. And it is not here. Okay, what is the other problem? There is a third problem, that is bulky size. Handling is difficult, costly. This is a lens for telescope. We need a large lens. 1 meter, 1.5 meter. What is lens made of? Lens is made of glass. What is glass? Glass is a type of stone. It is a transparent. So if you have this large stone, try to handle it and put it this way. You can't. We can't. On that stone, on that glass, we have to put a large rim of the steel, and that rim we have to fit in a pipe, and that there should be an arrangement of moving it. All this put together become very, very heavy, very bulky, and the handling is very difficult. This makes it very difficult for handling. So these are the, if you make large telescope, So these are the three shortcomings or the problems in reflection type of telescope. Then what can we do? Can we improve upon it? Answer is yes. And this is thinking out of the box. How? We say glass ko chhod do, we will use something else. And that is why we turn towards reflection type of telescopes to correct all these defects. So to correct all these defects, when we make reflection type, how do we correct it? So first, what is reflection type telescope? The answer is reflection type telescope. We use a reflector. A very simple reflector you have seen in your car headlight. In the headlight of car, there are reflectors. In the headlight of your motorcycle, there are reflectors. These are the reflectors. But if you see them very minutely, you will find that they are not spherical in shape, but they are parabolic. So we call them parabolic reflectors. Okay, you might have seen their weight, very lightweight. Parabolic reflector, there is a polish inside. Now, what are the benefits by using parabolic reflectors? The light is coming from the star. We make it very large. So, the size is no objection. If we make it 2 meter large, even the weight will not be much because we use very small, very thin sheet. So these are lightweights. Now, because of this shape, parabolic shape, how the reflection takes place. In parabola, in mathematics you might have studied, otherwise remember it. The parallel rays coming to the parabola, whether they are at the corners, whether they are at the middle, whether they are close to the pole, all these rays will meet at a single point called focus. So, what is removed? The answer is spherical aberration is removed. So, no spherical aberration. All parallel rays meet at focus. Very sharp and bright image. Okay. So this spherical aberration is gone. Second thing. So what happened to chromatic aberration? How we correct it in this? The answer is there is no need to correct it, because what is the root cause of chromatic aberration? The root cause of chromatic aberration is refraction. What is root cause? Refraction. And here there is no reflection at all. This is the phenomena of reflection. And if there is no reflection at all, there is no question of separating the different colors. So that is automatically gone with the construction. So there is no chromatic aberration because of reflection. Due to absence of refraction, no chromatic aberration. No chromatic aberration. Okay, so this one corrected, this two corrected. And number 3, this is very lightweight. This we can fit in a frame and rotate it anywhere. You have seen the headlight reflector of your motorcycle? If you take that large a lens, it will be very heavy. But if you take reflector of the motorcycle, it's very light. Only reflector part. So this is very light and this can be used for this purpose. And why do we use large objective in telescope? The answer is we were using large objective to collect a large quantity of light coming from that object. This thing was essence of telescope, and this can be very much fulfilled by this, because this we can make very large without increasing weight. So this we can make very large, so many rays can be collected at one place. So it has got all the advantages. So now this is the modern thing. We are using reflector type of telescopes. Now this reflector type of telescope, we can make a little bit correction in the diagram, and we will see how we actually see the image. Okay, this is a Kshetrapal type telescope. The rays, these parallel rays, are coming from far away object, from far away star. These are reflected and go towards focus. But before they reach focus here, we put another small reflector. This is very small reflector, so it does not obstruct all these rays. So most of the rays come here, get reflected. Just before the focus, we put a reflector. Again they are reflected, and we adjust this curvature in such a way that after this reflection, the rays are coming here, and here we put an eyepiece. This is an eyepiece to magnify the image, and from here we see it with the eyes. So inside, here we see a large image. This is the eyepiece we use here, like we use eyepiece in microscope and other type of telescope, like that. Image is formed here. This image is very, very bright image. No color aberrations, no spherical aberrations. At one place, a very bright image. Now we magnify it with a eyepiece and study it here. So this is Kshetrapal telescope. Okay, so now this Kshetrapal telescope, Newton also made his own telescope on the same principle. It was like this, that in a tube, the light, here he will put one reflector. This is parabolic reflector. The light is coming from this direction. It is reflected. When it is reflected back, he put a plane mirror here. Plane mirror at 45 degree. If it is plane mirror at 45 degree, then what will happen? These rays will be reflected by 90 degree here. These are reflected by 90 degree here. Then he put a prismatic eyepiece here and observe it from here. This is the only difference he made. This eyepiece was a good eyepiece made of many lenses. This in itself was a small type of microscope. This we used as eyepiece, which will make the image very large. So many light rays like this, but the basic principle is same. We have to collect many rays to make a very bright, sharp, colorless image. And that image we see in Kshetrapal. In this method, we make a little hole here. From that hole, this thing comes. And this hole is a very small one compared to the total area of this parabola. So there is not much effect on the number of rays, number of brightness. The same thing is used here. That this was done by Newton. So this was Kshetrapal telescope, this was Newton's telescope. So these are reflector type telescope. What is the question asked in this? The question in the examination is asked is, what are the benefits of reflector type telescope over refraction type telescope. What is the benefit of reflector type telescope over refraction type telescope? So minimum 3 points you have to give. Chromatic aberration, not here. Spherical aberration in refraction, not here. Very easy to handle because these are lightweight. And the aperture can be made very large so that total number of rays and the brightness of the image is much more. So this is all about telescope. And one small thing about telescope and microscope we have not done in both, that is resolving power. Resolving power we have to do when we have already studied wave characteristic of light. In the wave characteristic, first we will have to study the features of waves, and then only we can study about the resolving powers, and that we will again take up in that chapter, not here. So here we have studied their construction, their magnifying power, their features, dependence upon focal length of the two. And in the other classes we will do some numericals on this also. Thank you.